Again, this nice diagram that you compare the 4 basic categories of materials based on tensile strength. So tensile strength in megapascals. As we expect, metals and alloys are pretty high, polymers are pretty low. Ceramics generally are high in tensile strength, right? Generally high. Most of these are higher than general metals, but only one very special material, 4140 quenched and tempered, is very different. So some very special alloy steels can have a strength which is higher than ceramics, but ceramics are generally higher, and of course polymers are low. And then composites, because they are mix up, so they go from very low to middle to high composites, right, and so on. The next material property that we can take from the stress strain diagram is the ductility. So again, without reading, don't read, just pause and try to give me a word. What is ductility? What is ductility? If you see, we have described ductile behavior, brittle behavior when we started stress and strain. So now if you have to say one word, what is ductility? What is ductility? What will you say? Don't look anywhere, don't look into the notes, pause my lecture, video lecture, and try to answer in your mind, because you already knew it in previous courses. Then we defined it again for you when we started a stress strain diagram. So if you have to say one English sentence about ductility, not ductile or brittle, ductility, it is a property of a material. So what is ductility? If you have to say, it will be the ability of a material to undergo plastic deformation before fracture. Do you understand? The ability of a material to undergo plastic deformation before fracture, right? That if there are ceramics type of brittle materials, they can take a small load or they can take a very high load, but they don't plastically deform and suddenly break. But if it is a normal metal, then it will go through a large plastic deformation before it breaks. So the ability to have large plastic deformation, this is ductility. Okay? And how do you measure it? How do you measure it? We are showing you one thing called percent elongation, right? The heading, percent elongation. So percent elongation is just change in length upon original length, but as a percentage. Change in length upon original length. Tell me, what is this? Forget about this name. You know delta L upon L naught. What is it called? Yes, you are right. It is called strain. It is called strain. Change, but this is not change in length. Total change in length. Final length minus initial. So total change in length. Not any delta L. Not delta L at any point. Delta L at the time of fracture. When it fractures, what is the total change in length divided by the original length? You get the total strain multiplied by 100. That is the only thing. Multiplied by 100, you call it percent elongation, because that is exactly what it is. It is the total change in length before it fractures, given as a percentage. Given as a percentage. So here we are showing you, right, that you have your sample. You have your sample. This is the original cross section area, this is the original length, and you keep on elongating it under tensile load until it breaks. So this is the final length now, and there is a final area which we don't use, but the final length minus the original length is the total change in length divided by the original length, right? So you find actually the total strain, the maximum strain, and multiplied by 100. And we are just showing you that if this is a brittle type of material, there will be very small amount, and if it is a good ductile material, there will be a large amount. Forget about this line. I mean, just drop the line perpendicular here. This is, remember, just to find out that if we unload it, offload it, then what will happen. But if you just drop a line perpendicular here, then this is the strain at fracture. And here, if you drop a perpendicular line, this is the strain at fracture. So the strain at fracture multiplied by 100 is just a percentage value. So maybe the strain at fracture is 0.25, and when you multiply it by 100, it is 25%. So 25% is the percent elongation, and this is the ductility of the material. One material has 10% total elongation, the other has 20%, the other has 30%. So whichever has higher percent elongation is more ductile. Okay, it deforms much more before fracture. There is another way we can define ductility. You see, when the length is changing, the area is also changing, isn't it? We have seen that the length increases, the diameter decreases, so the area decreases. So in the change in length, you say maximum increase in length, but in terms of area, the reduction in area, because the original area is large, once under tensile load you extend it, then the area keeps on going down. So if you measure the area originally, A0, original area, and you measure the area finally, so the final area is much smaller. The change in area divided by original area is now percent reduction in area, But this will not be final minus original. Final is a small value. So if you write final area minus a small initial, then it will be minus, negative, right? Therefore, initial area minus final. But this is the total change in area at the point of fracture. At the point of fracture, what is the area there? We showed you in the previous diagram. So if you have A0 and AF, then change in area upon original area multiply by 100. So this is another way of finding the ductility. Any material that shows more change in area is more ductile, of course. Of course, the percent elongation number and the percent reduction in area number will not match. They are two different numbers. But if you are comparing different materials on percent elongation, then it is okay. If you are comparing different ones on percent reduction in area, then you are okay. But it cannot be that you give percent elongation for one material and give percent reduction in area for the other material. Then you cannot, right? Here we are just giving you the reason, right? That ductility decreases due to the presence of defects such as porosity or inclusions and so on. You see, if in the material there are certain porosities or inclusions or problems, then it will break earlier, right? The material already has some cracks and so on. So it will break earlier. So it will not go to as much ductile point as is there. So the percent reduction in area or the percent elongation will be low, that ductility will be low if the material has some defects inside.